Hello, I'm Aryan Agrawal, a high school senior from California. Today, I'll be presenting my research on DrugAI, a framework using generative adversarial networks for de novo drug discovery. My focus is on generating novel inhibitors for the AKT1 protein, which plays a key role in cancer treatment. I'll walk you through the DrugAI framework, its experiments, results, and potential future directions. One major challenge in drug discovery is a vast chemical space, containing over 10 to the 60 potential compounds, but only a few can effectively bind to a specific protein. Traditional methods like high throughput and virtual screening struggle to explore this vast space efficiently and often rely on known ligands or protein structures. To address these limitations, AI-driven approaches are essential. Generative models such as GANs combined with graph transformers allow us to design new drug-like molecules by learning complex relationships between compounds and target proteins. These models help generate molecules optimized for specific biological targets, which is the focus of my research. So what is GAN? The GAN operates with two competing neural networks, the generator and the discriminator. The generator analyzes the training data, identifies key molecular attributes, and then introduces noise as a random change to generate new, fake molecules. The discriminator independently learns the characteristics of real molecules from the training set. It evaluates the fake molecules generated by the generator, calculating the probability that these belong to the original dataset. Based on the discriminator's feedback, the generator refines its process, gradually producing more realistic, chemically valid molecules. The two networks improve over successive cycles. The discriminator provides feedback to the generator, guiding it to reduce unnecessary noise and refine the molecular structures in each round. Moving to the model architecture, DrugAI is built on a multi-phase GAN system, consisting of three sequential GANs: seed GAN, bind GAN, and filter GAN, each serving a unique role in the drug discovery process. Seed GAN generates the initial molecular structures by learning the distribution of molecular properties through graph transformers. It outputs a rough molecular graph, which acts as a starting point. Bind GAN takes these initial structures and optimizes them for interaction with a specific target protein, in this case the AKT1 protein. It incorporates both molecular data and protein structural features to ensure strong molecular binding interactions. Finally, filter GAN ensures that the generated molecules meet essential drug-like properties, such as pharmacokinetics and pharmacodynamics, filtering out molecules that don't meet these criteria. The entire process is powered by graph transformers using multi-head attention mechanisms in both the encoder and decoder to capture complex relationships in molecular graphs. The encoder learns the structural representation of molecules by processing annotation and adjacency matrices, while the decoder refines these representations by integrating protein features. This allows for a more accurate generation of drug-like molecules that are specific to the target proteins. We used three datasets: compound data from Chembo version 34, protein structures from the Protein Data Bank, and bioactivity from Chembo and DrugBank. We explored four model variations: DrugAI PSM for protein-specific molecule generation, RIB for inhibitor-based molecules, RL using reinforcement learning to enhance diversity, and no target for general drug-like molecules. To evaluate the model's performance, we employed the Moses benchmarking platform, which measures metrics like validity, uniqueness, novelty, and internal diversity of the generated molecules. We performed molecular docking studies on the top 100 generated molecules to assess their binding affinity, focusing on the interaction with the AKT1 protein. The docking scores indicated that DrugAI RIB generated molecules had better binding affinities than the native ligand used in the AKT1 structure, showcasing the model's ability to design molecules with strong target-specific interactions. In this study, we developed the DrugAI system, which integrates GANs with a graph transformer architecture to generate inhibitor candidates for specific target proteins. Our computational analyses demonstrated that these de novo molecules have strong potential for effectively targeting the AKT1 protein. As a next step, we plan to enhance DrugGen by A. Training on a larger, target-centric dataset, incorporating additional proteins and their real inhibitors, and B. Increasing the model's parameters to optimize performance further. I hope you found this presentation insightful. Thank you for watching.